This is section 9.5, alternating series. Now let's recall, we have learned several tests to determine whether a series converges or diverges. Now, in this section, we will learn another type of series. Okay, so we can determine whether it converges or not quickly. This is called the alternating series. Now, first of all, the series that we consider, most of the time, it contains all the positive terms. Now, there are times we have series that have the term that is positive and negative, and usually it will be alternately positive negative. For example, if I have, say, negative 1, right, to the n power time, say, n plus 3, and from 1 to infinity. Now, if you look at this formula, there are two parts. So this part right here is a formula that's containing positive number, right? So plugging 1, 2, 3 is a positive. But the negative 1 to the n will have the powers. You see the negative 1 to the power. So when you plug in 1, it'll be odd. So the negative 1 to the first power will be negative. So you're going to have negative 1 plus 3 is 4. Okay. Then if you plug in 2, negative 1 squared, that will be positive. And 2 plus 3 is 5. So you have positive 5. And then the next term is negative 1 to the third. It's odd, so we negative again. And then 3 plus 3 will be 6. So you can see it will be alternate positive, negative, positive, and negative. Then the next one will be negative 8, and then so on. Okay, so any series of this form is called alternating series. Okay, so again, the sign has been alternately changed from positive to negative because of the n powers of the negative 1 base. Right? So we'll be interested in knowing, in this case, whether the series converge or diverge when you have the signs alternately changing, right? So let's look at the actual definitions. An alternating series is a series whose sum, okay, whose terms are alternately positive and negative. Okay, so it must have one of the following forms. Either you have negative 1 to the n powers, the one that we had earlier, right? Negative 1 to n, and then there's an a sub n term there, so that's a positive terms formula there. Or you can have negative 1 to n plus 1. Sometimes n minus 1 or n plus 1. They actually the same. You write it out. It just depending on where we start with the index n, and the term may start with a negative term first or a positive term first. Okay, so if you look at the series right here, we call it alternating harmonic series. Negative 1 to the n over n. Okay, so summations there. So does the series converge or diverge? Now, again, if you write down or write out the all the terms, just get the feel of what's the term look like. That's negative 1 to the n, right, over n, and from 1 to infinity. Plug in 1, right? So negative 1 to the 1, so the negative 1. So you have negative 1 over, this is 1. When n is 2, negative 1 squared, it's positive 1, so it's positive 1 over 2. And then the next term, you're going to have 3, negative 1 to the third is negative, so negative 1 over, and that's 3. And then you have 1 over 4. And then you have negative 1 over 5. Continue. So you can see that the terms are ultimately positive, negative. Now, does this series converge, diverge? Well, it's hard to tell because now we don't have the test to determine whether converge diverges yet. Okay, but if you compare to this is called harmonic series, by the way, the one that we learned earlier. This one over n. See, that's why we call harmonic alternating harmonic series, because it's really the harmonic series. The one that we learned is 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5. You see, it's all the terms are the same, but they are positive here, but the signs are alternating, changing, right? Now, the series down here we know is called the harmonic series and hence diverge. Now, this series, it's actually smaller than a series in terms of sum because they have some negative terms. So every other term is negative. To make the sum, it's actually smaller. It turns out this series here converge, okay? The series here, the alternating harmonic series converge. So that one converges. The harmonic series down here diverges. But how do we know? All right, so here's a quick test to do. If you have a series, alternating series, where if you ignore the negative side, so make that positive, so let's look like this, okay? When you see the term is decreasing, so you have, so if you're ignoring negative, turn it positive, so 1 half, 1/3, 1/4, 1/5, it's decreasing. Moreover, it's getting closer and closer to 0, right? If n getting bigger and bigger, this is going to approach 0. If these two conditions are met, then the series must converge. And what we call, this is what we call a alternating series test. Okay, so here it is. A series of the form, all right, so either form, doesn't matter, will converge if, number 1, the limit of a sub n equals 0, and when n go to infinity, and a sub n plus 1 less than a sub n for all n. Right, so what this means is if you plug in 1, right, so it'll be a1 bigger than a2. You plug 2 in, then a2 is bigger than a3. Plug 3 in, so a3 bigger than a4. So again, what this statement means, the term is decreasing, right? 1 half, 1/3, 1/4, 1/5. So equivalently, we're saying that the sequence is actually decreasing. Okay. Now, just look back at the example we have up here, that series here, right? So I told you that it converges, but here's what we're gonna do using the test. Okay, so again, looking at that same series, number 1. Okay, so if you use this test, you need to identify the a sub n. Okay, so it's a sub n. Again, the a sub n is just the terms without the -1 to exponent part. Or in other words, it's just the positive terms of the series. So if you look at this series right here, if you take away -1 to the n, then your a sub n is really 1 over n, isn't it? Or let me make it precise. You can rewrite that as -1 to the n power times 1 over n, and from 1 to infinity, right? So you can see if I rewrite it this way, this is an alternating series. When I say alternating series, I need to identify the a sub n. This one, right? So a sub n in this case is 1 over n. And then we're going to proceed to check two conditions. One is whether the limit of the a sub n 1 over n and approach infinity, is it equal to 0? Let me change labeling. Guess I want to call this condition 1 here. Okay, condition 1. You need to check condition 1. Limit 1 over n go to 0. Oh, is it true? Yes, right? If n goes to infinity, the fraction is going to approach 0. So that definitely check. Right? Then you check condition 2. The condition 2, you are trying to check to make sure that a sub n plus 1 less than a sub n. Is it true? What is a sub n? A sub n is 1 over n. What is a sub n plus 1? So replace n with n plus 1. So that is 1 over n plus 1. See this? I'm checking the a sub n plus 1 less than a sub n. In this case, 1 over n plus 1 less than 1 over n. Is it true? Yes, because the denominator here is bigger. So the fraction is going to be smaller. Check. If these two checks, then by the alternate series test, we can conclude that the series that we're testing, -1 over n, or equal to n over n, that series converges. Okay. And by alternating series test. Okay. That's alternating series test. All right. So that is this problem right here. Now, if one considers the next example, it's very well. It's a bit different now. It's you have -e to the n over 7 to the n, so it's not quite fit the form yet. Okay. I'm going to do it here. What should I label? Maybe I label this is A. That's an example B. Right, so that's my example A. And then I have the example B. Right, so this series. Again, I can rewrite this to match the formula. -e to the n is the same as -1 to the n times e to the n. So you kind of split into two different bases, raised to the n powers in multiplications. You could do that, and that is n from 1 to infinity. And again, you can see we recognize that is an alternating series. Notice that I didn't write out the terms. If you want, you could. You can see the size alternating. But as long as I see -1 to the n power or some n plus 1 power, then you know that the series is an alternating series. And therefore, I can use the alternating series test here. In this case, the a sub n is a bit complicated. It's e to the n over 7 to the n power. Okay. Now checking conditions. Check condition 1. Well, condition 1, it's a limit of, what's a sub n again in this case? Here, e to the n, 7 to the n. So you have e to the n and 7 to the n powers. Is it limit equal to 0? Well, it's not clear in this case if you leave it that way, because when n go to infinity, e to the n, that's go to infinity. The denominator, 7 to the n, is also go to infinity. So the numerator is getting bigger and bigger, denominator is also getting bigger and bigger. So what's the ratio approaching? Well, we don't know. So in this case, we got to do a little bit of work. How about combining into one base? Because they have the same exponent n. If you write it this way, how about e over 7 to the n power? E over 7. Now, e over 7 is just a constant, right? The e is constant over 7. In fact, it's less than 1. Right? The e is only 2.78 over 7. So this is the base is smaller than 1. Now recall in exponential functions, if you have something raised to the n power, if that constant, if that base is smaller than 1, then raising to the larger and larger n, this will get smaller and smaller, and hence its approach 0. Okay. So that's from the exponential function point of view. I can check that. For condition 2, checking a sub n plus 1 less than a sub n. Now again, what's a sub n? A sub n is e to the n over 7 to the n. All right, so what's a sub n plus 1? We replace the n with n plus 1. That's e to the n plus 1 over 7 to the n plus 1. Okay, now which side is bigger? Is it true? Well, the numerators on the right is smaller than the numerators on the left. See that? This is this bigger exponent. So although the denominators here is larger, make the denominator, make the fraction smaller, but the numerator is bigger. So I mean, I cannot tell from here. So one way to do is we can simplify using the algebra. In this case, when you rewrite e to the n plus 1 is the same as e to the n times e to the first power, right? So that's equivalent. 7 to the n plus 1 is 7 to the n times 7. And then you have e to the n over 7 to the n. Okay, it's less than still. Again, I'm checking to see if it's true. Now, you can think of canceling if you want, or maybe multiply both sides by the reciprocal of these fractions. Okay, so this one got canceled, that's one got canceled. So what do you have left? So you got 1 on the right, and therefore this is equivalent to e over 7 less than 1. Okay, after you canceling everything, so e to the 7 less 1, is that true? Yes, because that numerator, I mean that fraction is smaller than 1. right? So I verify that. And then from these two, we can make a conclusion. We can make the conclusion that the series converges by alternating series test. All right. Now, the two examples that we did, the two conditions are met. The second example a bit harder to verify. But the question is, what if these two conditions are not satisfied? Right? So here's some remark. Number one, if condition one of the alternating series test fails, divergent test should work. In other words, if the limit of the a sub n is not equal to 0, then the divergent test will work and the series will diverge. Okay. If condition 2 fail, okay, then we cannot make any conclusions about the test. It might converge or might diverge, who knows. We have to try different methods or different tests. Okay. And the third remark here, sometimes verifying the condition, you see that it's not easy. This one we still manage to do it by simplifying algebra. You can see this is actually true. But if we can't, then we might have to use the first derivative to show whether the series or the sequence is decreasing. Now, don't forget that the condition 2 is just saying the terms are decreasing. So if I want to show that it's decreasing, I can show that the function is decreasing. How do I know the function is decreasing? Well, the derivative. Remember the first derivative test. If you can show the first derivative is negative, less than 0, then you know the function will, whatever the function of x, will be decreasing. And that should, should our purpose be checking whether the function is decreasing. Okay. Now let's look at these examples here. The first one here, we have this series, right? -1 to n minus 1 n squared over 1 plus 2 n squared. So again, as always, you're going to identify whether this series is a alternating series first. Well, it is, because it has this formula -1 to n minus 1 there. So I know that this is an alternating series. Now, when it's alternating series, make sure that we need to identify the a sub n. What is a sub n in this case? Take away the -1 to n power part, you got n squared over 1 plus 2n squared. Okay? First conditions we check is taking the limit. Taking the limit of a sub n, which is n squared over 1 plus 2n squared. And when n approach infinity, well, this is the rational, right? Second degree over second degree. So it's 1 over 2. It's equal to 1/2. So you see that the term does not approach 0 as required by the alternating series. However, since that's not equal to 0 by the divergent test, if you take the limits of this whole thing, that will not approach 0, and therefore the series would diverge. Okay. Series diverges. Look, number 2, 1 over natural log of 2 minus 1 over natural log of 3, and so on and so forth. Now, you see that clearly that series is a alternating series with the size alternating. So it is an alternating series. It is an alternating series. If it's alternating series, then what is A sub n? Again, A sub n is just a positive term if you're ignoring the negative, and you can see, well, it's 1 over, right? It's 1 over natural log, and number is increasing, so natural log of n. Alternatively, you might want to write the formula first, although it's not required. You see that will be 1 over natural log of n, but in this case, it's going to be -1 to the n, 1 over natural log of n, and start at 2 here, 2, right? 2 to infinity, right? So you plug 2 in, you got that one 3, and you got this term, and so on. But you see this on the A sub n. Now, once you identify that, then we will check 2 conditions again, right? So the conditions, one is what's the limits of 1 over natural log of n approach infinity? Is that equal to 0? Yes. How do I know? Because the n's in the bottom, if n approach infinity, this denominator getting larger and larger, the numerator stayed the same, so it must approach 0. The second condition, again, you're going to checking whether it's 1 over n, as our A sub n, or 1 over natural log of n, less than 1 over natural log of n plus 1. Right, again, is it true? Yes, because the numerator is the same value, the denominator. This denominator on the left is bigger, so the fraction is much smaller. So that check. Again, these two combine, we can conclude that the series converges by alternating series test, right? So that should finish the this part 1. Well, let me go ahead and do number 3. There's one more example here. Example 3, a little bit harder. You can see, you can recognize this ordering series easily, right? But then the A sub n, it's also easy to recognize, which is that part. Okay, so that is an alternating series with a sub n equal. Now notice this is nq times e to the negative 2n. Now to make it easier, I don't like naming exponents. I can rewrite that as nq over e to the 2n. It's the same with positive, negative power means reciprocal, right? Right, so again, we're gonna check two things. We're gonna check whether the limit of nq over e to the 2n and approach infinity is 0. Now, again, when n's on the top and the bottom, it's very hard to tell if you have n of numerator denominators, because top and bottom both approach infinity. So to do this, you might have to recall the L'Hopital rule. So let's switch that to the functions notation. Instead of n is an integer, so think about this as a function xq over e to the 2x, where x approaches infinity. Now, when x go to infinity, the bottom go to infinity, right? So numerator, denominator go to infinity. In that case, we can apply the L'Hopital rule. It helps there. And by the L'Hopital rule, we just take the derivative of the numerator, that's 3x squared, over the derivative of the denominators, that is e to the 2x times 2. X approach infinity. Now, because the numerators again approach infinity, denominator approach infinity, I can apply the L'Hopital rule again. Take a derivative, I have 6x over 2 e to the 2x. By chain rule, there's an extra 2, so it's times 2, and x approach infinity. And once again, you see the numerator and denominator approach infinity. But I can repeat with the L'Hopital rule one more time. And I see this will equal to what? To become 6 derivative. And that becomes still the e to 2x times an extra 2. The denominator now have an x on top that stays constant. You can see it will approach 0 there. So we can skip that little steps there. And hence it satisfies the condition 1. Now condition 2 is not quite, it's not easy to check either, because I'm going to check a sub n less than a sub n plus 1. This is the way, the case where I will not compare it side by side, because it's hard to do when n's on top and bottom. So instead, to check that, I'm going to consider the functions. Think of that as a function again, where you have xq over e to the 2x. And I want to make sure that this is actually a decreasing function. Okay. So to do that, you're gonna take the derivative f prime of x. This is the, by the way, the quotient rule. Derivative xq is 3x squared times e to the 2x minus derivative of the bottoms is e to the 2x times 2 times the numerators is xq, okay, or over e to the 2x quantity squared. Again, using the quotient rule. Now, the numerator has e to the 2x in common. It has actually x squared in common. I can take out e to the 2x as well as x squared. What I have left is 3 minus 2 x cubed. You take out x squared, you have an extra x there. It's all over e to the 2x squared. It's actually e to the 4x. But I'm going to write e to the 2x times e to the 2x separately, right, square. So you can see there is a cancellations there. Okay. Now the question is whether this quantity less than 0. Remember when the derivative be less than 0, so the function is decreasing. Now the x squared is always positive. That's always positive. So if this quantity is negative only when the 3 minus 2x is negative or less than 0. Solving for x, I have 3 less than 2x or 3 half less than x or x greater than 3 half z, right? So that means if x is bigger than 3 half, this less than 0, the derivative less than 0, and hence it's negative or decreasing. And notice that with now n start at 1. So yes, when x bigger than 3 half, so from 3 half on, all the term will be decreasing, and therefore I can combine here. Okay, so that checked when x bigger than 3 half. So here I can conclude the series converges by alternating series test, right?